Search in rotated sorted array. Let's raise the stakes. What if the array you're searching in is sorted, but then suddenly rotated at an unknown pivot? Search in rotated sorted array is a Pattern Mastery 100 superstar and a go-to interview question at Google, Facebook, and Apple. So many candidates try to flatten the array or revert to brute force, but with the right approach, you can use binary search to find any target in O log n time. Mastering this pattern proves you're ready for real-world coding challenges. Let's see how it's done. Let's break it down. You're given a sorted array that's been rotated at an unknown point, and a target value. You need to find the index of the target, or return -1 if it's not present. No duplicates, and the array is still mostly sorted, just with one pivot. Now let's assess. Scanning every value is not good enough for large arrays. Because the array is made of two sorted halves, we can adapt binary search. At each step, we determine which half is sorted, then see if the target lies within that half. This halves the search space each time. Classic O log n efficiency. Here's the structure. First, set left and right pointers at the array's ends. Then, while left is less than or equal to right, find mid. If nums at mid equals the target, return mid. If nums from left to mid is sorted. If the target is in this half, move right to mid -1. Else, move left to mid +1. Otherwise, meaning the right half is sorted. If the target is in this half, move left to mid +1. Else, move right to mid -1. Finally, if not found, return -1.
Let's try to implement it using Solution 1. We begin by creating a class named Solution. This is just the container that holds our function. This defines our function search, which receives a list of numbers called nums and the value we're trying to find, called target. Our goal is to return the index where the target appears. Here we loop through the list one element at a time. I is the index, and x is the current number. This loop checks each value in order. Because it touches every element once, it runs in O of n time. We compare the current number with the target. If they match, we know we found the position we're looking for. So when a match is found, we immediately return the index where the target appears. If the loop finishes without finding the target, we return -1. This signals that the value does not exist in the list. And that's how this algorithm works. It loops through the list from left to right, then returns the index as soon as it finds the target, or -1 if it doesn't. Efficient, simple, and elegant. Check. Here's the verification for this rotated array search test case. Input is nums equals 4, 5, 6, 7, 0, 1, 2. Target equals 0. Nums is a sorted array that has been rotated, and our task is to locate the index of the target. Let's walk through what this means. The array starts off increasing, 4, then 5, then 6, then 7. Then it suddenly drops down to 0. That drop marks the rotation pivot. After that, it rises again. 0, then 1, then 2. Since 0 is the target, we look for the position where it appears. Inspecting the array. Index 0 gives 4. Index 1 gives 5. Index 2 gives 6. Index 3 gives 7. Index 4 gives 0. Index 5 gives 1. Index 6 gives 2. The algorithm, binary search adapted for rotation, also finds that the target lies on the pivoted side. It eventually narrows down to nums at index 4. So the returned answer is, the output 4 matches the expected 4. This confirms the search function works correctly on this rotated sorted array. Now let's try another implement approach using Solution 2. We begin by defining a class named Solution 2. This simply holds our function. This sets up our search function, which takes a rotated sorted array called nums, and the value we want to find, called target. Our mission is to locate the target's index using binary search. We create two pointers. L starts at the left end of the array. R starts at the right end. These will frame the current search window. We continue searching as long as the left pointer has not passed the right pointer. Since we're having the search space each time, this loop runs in O of log n time. We compute the middle index of the current search window using integer division. This midpoint helps us decide which half to keep. We check if the middle element is exactly the target. If so, we found the answer. When we find the target at the midpoint, we immediately return its index. This condition checks whether the left half of the array, from L to mid, is sorted. In a rotated array, one side is always sorted. We just need to identify which. If the left half is sorted, We check whether the target lies inside that sorted range. If it does, the target must be somewhere on the left side. So we move the right pointer to mid-1, shrinking the window to the left half. If the target is not in the sorted left half, it must be in the right half. So we move the left pointer to mid+1 to shift our search to the right half. This branch means the left half was not sorted, so the right half must be sorted instead. We now check whether the target lies within the sorted right half. If it does, we narrow our search to the right side. So we shift the left pointer forward to focus on the right half. If the target is not inside the sorted right half, then it must be somewhere in the left half. We move the right pointer left to search the unsorted half on the left side. If the loop finishes without finding the target, we return -1 to indicate that the value is not present in the array. Final summary. And that's how this algorithm works. It sets up left and right pointers, then uses binary search to determine which half of the rotated array is sorted, and where the target must lie. It keeps narrowing the search space until the answer appears. Efficient, simple, and elegant. Check. Let's walk through this test case for the search in a rotated sorted array problem. Input. nums equals 4, 5, 6, 7, 0, 1, 2. Target equals 3. Here, nums is a rotated version of a sorted array. Our goal is to determine whether the target exists, and if so, return its index. If it does not exist, we return -1. Walking through what the array shows us. The first portion, 4 then 5 then 6 then 7, is increasing. Then we hit the pivot where it drops to 0. Then it continues increasing again, 0 then 1 then 2. Now look for 3. It is not in the first block, which is 4 through 7. It is not in the pivoted block, which is 0 through 2. There is no position where 3 appears in the array. The binary search logic also confirms this. When checking each sorted half, 3 never falls into any valid range. Eventually, the algorithm exhausts the search space and returns -1. So the correct output is -1. The output -1 matches the expected -1, confirming that the algorithm correctly identifies when a target is not present in a rotated sorted array.
Let's have a quick recap. Breakdown recap. This problem takes a sorted array that's been rotated at an unknown pivot and asks us to find a specific target value. The catch is that while the array looks broken, each half is still sorted, meaning we can use logic, not brute force, to locate the target efficiently. Assess recap. At first glance, it's easy to fall back on a linear scan, but that's ON time, too slow for big inputs. The key insight is realizing that even after rotation, the array keeps a sorted structure in parts. By identifying which half is sorted during each step, we can adapt binary search to work perfectly here. Structure recap. The solutions flow revolves around 2 pointers, left and right. We repeatedly find the midpoint, check which half is sorted, and decide where to move next. If the target falls inside the sorted range, we search that half, otherwise, we shift to the other. Each step cuts the search space in half. Implement recap. When we ran the algorithm, the process played out like a guided binary search with added logic. At every iteration, we evaluated which half was ordered and adjusted our search boundaries accordingly. The code naturally zeroed in on the correct index, or concluded that the target wasn't present. Check recap. Testing the algorithm on our example confirmed the reasoning. The search quickly honed in on the target value of 8, found at index 5. Every comparison narrowed the field with precision, proving the O-log-n efficiency we expected from binary search. The biggest takeaway here is that patterns matter more than appearances. Even when an array seems broken, its underlying structure holds the key. Recognizing that lets you transform classic techniques, like binary search, into powerful tools for complex problems. Once you see this pattern, you'll never look at arrays the same way again.